Okay, so it's recording. Um, just checking the volume. It's good. All right. So we are basically looking into graphs now, and we are looking into algorithms that can find the shortest path from vertices between vertices. I'll put it that way. So in this case, we have a rather kind of interesting graph. I think I'll convert the format. So instead of arranging everything horizontally, I mean vertically, it will arrange it vertically. Okay, so give me a second here. It'll take about a minute to update, but it's not too bad. So instead of top down, it's going to be left right. So commit the changes, just because it's easy to display that way when it's spread horizontally. So we'll give it a minute or so to update. The two algorithms that we'll be talking about, one is called Dijkstra's algorithm, which is named after the person who invented the algorithm. The other one is just called the A-star algorithm. Both of these you can find on Wikipedia. So if you were to go to Wikipedia, you will find the Dijkstra's algorithm, Dijkstria. So this is Dijkstra's algorithm, and it even has a kind of animated show to show you how things are updated. So we are going to do that. Okay, we will do all the tracing in this class. Once I present the algorithm. It is a search algorithm. It is also called a greedy algorithm, and I'll explain why it is called a greedy algorithm in just a moment. And then they also have the big theta. This time it is correct. Okay, it is the type bound, which is the number of elements in the set of edges, plus the log of, not the log, but the cardinality of the vertices times the log of the vertices. So that's kind of like a type bound of how much time it takes for the algorithm to finish. And this addition here means that if there are more edges than there are vertices, then this becomes the major component. And then this side, oh, I take it back. If there are more edges than there are log v, okay, the number of vertices times the log of the number of vertices, then the number of edges becomes the actual upper bound. Okay. All right. So are we ready to go over the algorithm? Maybe. Okay. So we're going to take a look at the graph first, because we need to talk about a few terms. So I think this one looks better, okay, just because everything appears on the same page. So we have A, B, C, D, E, F as vertices. Essentially, a vertex is a node, okay, so to speak. If you're taking CISP 430, it is kind of like a node in a tree, except a tree is only a kind of graph. Okay, a graph is not necessarily a tree, but a tree is always a graph. So the numbers going on these edges, they are representing a distance. In other words, if I were to go from A to E directly, it will cost me 10 units of whatever. Okay, so a lot of times, if this is for transportation, it's going to be either the amount of time or fuel cost, or just a cost of everything added together, including insurance, fuel, time of the driver, and so on. You can even have loops here. Okay, so you can see how A goes to B and then B goes back to A. The algorithm can handle loops without a problem. Okay, and in this case, when you see a double circle, it means it is a destination. So every other vertex is not a destination, and we want to figure out what is the shortest path from a it can be a destination, but it will be kind of pointless. So we want to figure out the shortest path from any vertex to a destination in this case. So there are two destinations. So we are basically just asking, okay, so which one is the closest? What is the shortest path to the closest destination? So are we doing okay so far in terms of the purpose of the algorithm? Has Iraj started to talk about Dijkstra's algorithm in his class? Not yet? Okay. So if I remember correctly, his algorithm finds the shortest path from a particular vertex to a single destination. I modified that algorithm a little bit, so now it will find shortest paths from every vertex to the closest destination. Is that okay? So when you run this algorithm, it doesn't just give you the shortest path from a particular vertex to another vertex, which is a destination. It shows you all the shortest paths from every vertex to the closest destination, which is kind of cool, okay? Because if you apply that, okay, so think of all those double circles as bathrooms in Six Flags, okay? And then all the other nodes as non-bathroom intersections, on that map. It will find you the shortest path from every intersection to the closest bathroom. So it's kind of cool, okay? I think it's kind of cool. All right, so the algorithm itself, so we'll get back to this picture in just a little bit, and I'll talk about the algorithm first, okay? So the algorithm, this doesn't look good. I know why it looks like that too. I'll fix that when I get to that point. That looks bad too. The reason why it looks like this has to do with underscores are not processed correctly in this engine. So there are several places where things they don't get represented correctly. So, but since we're focusing on Dijkstra's algorithm, we can just focus on this one. The other page still works, okay? Unfortunately, I have changed my link to point to this page, and I don't want to waste your class time to fix the document. So I'll fix it after class. All right, so we'll start with the algorithm. The givens is a graph. So the graph is given to us as a set of vertices. So in the picture that we saw earlier, everything that is either in a rectangle, a round edge rectangle, and also in a double circle, those are our vertices. The arrows going from one vertex to another vertex, those are our edges. So when we go back to the algorithm, so now that we kind of know what it looks like, okay, so V is the set of all the vertices, and then E is all the edges. D is a function. It maps each edge to the cost or the distance of that particular edge. So R has a little asterisk here to mean that we only care about non-negative real numbers. In other words, no edge can have a negative distance, because that means we want to go for infinite loops if there's an infinite loop with a negative distance, which really does not make sense in real life. And then we'll designate as a set that is a subset of all the vertices, and that is a subset of vertices identified as our destinations. In other words, in our graphs, okay, if I go all the way back to our graphs here, the destination set S will consist of E and F as elements. When A, B, C, D, E, F, they are all in V, because that is a set of all the vertices. So are we doing okay so far? Differentiating between the set of vertices, which is A, B, C, D, E, F, every single point, as opposed to the set S, which is really just the set of all the destinations. In this case, the set of all the destinations only consists of E and F as elements. Are we good so far with just the symbols? Okay, all right. So I see some nods. So now we proceed with what else do we know? Well, we don't need to know any more than this. So that means these 2 points basically they summarize what we need to be given with in order for the algorithm to work. So the algorithm has some initialization code. The initialization code is basically saying for every vertex in S, which means these are all destinations, L of V is defined to be 0. They're initialized to 0 because the uppercase L destination is the length of the shortest path to the vertex that is applied as the parameter. So it kind of makes sense here, okay, because if V is an element of S, that means V is a destination by the definition of S. If you're already at a destination and I ask you what is the length of the shortest path to a destination, what would that be? You're already at a destination. In other words, imagine that you are the chaperone again, okay, and you're standing right in front of a bathroom. and a little child is asking you, I need to go to the bathroom. How long is it gonna take? You go like, we're here already. It's right here. So that means the distance of the shortest path to a bathroom is 0. Does that make sense? So when you're standing on a destination and you're asked what is the length of the shortest path to a destination, hey, I'm already here. So the length of that shortest path is 0. Is that okay? All right. So what about the rest? What about all the vertices that are not destinations themselves? So in that case, we kind of make a assumption that we don't even know whether there is a path to from that vertex V to a destination. So the length of the shortest path to a destination is initialized to infinity because we don't even know whether there is going to be a path between that vertex V and a destination. Is that okay? All right, okay. And then we do the initialization. Okay, Q is also a set. It is just a variable, a local variable when we run the algorithm. So the set Q is initialized to the set S initially. In other words, this is the initial set of boundary vertices that we have just an updated length to a destination. That's because we did this update here, okay? Because all the vertices in S, they all have a L value initialized to 0, which is a non-infinity. That's that's the reason why we put all those vertices into the set Q, because we will start from there. Okay, we'll try to figure out the length of the shortest path from all the other vertices to a destination, starting with the destinations. Are we doing okay so far with that? So one way to look at this is to think of a maze. Okay, so think about an enclosed maze where you have multiple spots. So you basically stick a live cockroach, at every intersection of this maze, and then with certain intersections, they are designated as ground zeros. Okay, where you put pesticide, like a pesticide bomb, at those locations. So the question now is, what is the ordering of the cockroaches dying? So the cockroaches who are at the ground zeros, where you have the pesticide bombs, they would die first. They would die immediately, and then the cockroaches next to that those locations would die next, and so on. So we are really trying to figure out how long does it take for a cockroach to die in that particular maze. Is that example working or not? Or are you guys just thinking, ew, cockroaches, I don't like cockroaches? No problem with that analogy? Okay, all right. This is not working because open and close curly braces is not processed correctly. I need double backslash to escape it. So E prime is initialized to the empty set. Okay, this part is supposed to be open curly brace, close curly brace. So that's how E prime is initialized. So eventually E prime becomes the solution. Okay, so I'll give you guys an example based on the graph that I showed you earlier. And this is also supposed to be the empty set. Okay, as long as Q is not an empty set, we have to continue with a while loop. Or do you guys want me to fix the code? Because I think it just looks ugly right now. I think I'll go ahead and fix it first, so you guys can kind of not look at the screen unless you want to know how I fixed all of this stuff here. I just did a conversion earlier, and that's why it's not working. Okay, we'll find all the occurrences with underscore, because that's one of the problem. All right, so with all of this, they need to be escaped, because otherwise underscore is understood. Oh, okay, I can show you something that's relevant to programming. I'm looking for underscores that are not yet escaped. So the way to do that in regular expression is to specify, anything other than a backslash. And I think backslash needs to be escaped, followed by an underscore. So this is specifying, okay, if something is already escaped, don't show me. I just need to look at everything that is not escaped. So we go for regular expression and then search for those. All right, so this one is not escaped. And that's it. Those are all the unescaped underscores. So now we need to look for unescaped or not sufficiently escaped curly braces or braces. So the escape character is still the backslash, and then we have one backslash which is already correct, and then followed by an open brace. So we need to look for that. Nope. Okay, let me specify that one more time. Okay, not. Okay, so the caret here inside the square bracket notation, this is regular expression, means anything other than what we specify here. So this is a backslash, because backslash itself needs to be escaped with another backslash. So we have another backslash which needs to be a part of the pattern, and then also the open brace, which also needs to be escaped because open brace otherwise has specific special meanings. And we're looking for regular expressions. Okay, so we look. All right, there we go. So this one needs to be double escaped. This one needs to be double escaped. I can also specify a replace pattern, but I'm just gonna do it manually just in case there are other ones that I should not escape. There we go. How many people already know about regular expressions before this class? Okay. They are really handy in different types of context. There are editors that understand regular expression, which means when you're editing your program, you can potentially look for patterns and replace with other patterns if you know how to specify the patterns. So I'm just doing this manually. There we go. All right, we are close to getting this all done. Okay.
There's one at the top of the screen there too.
Hmm?
There was one at the top of the screen too. On that last one. So you skipped one. You already skipped that stage.
I skipped that. Okay. Well, let's see if we can find it once we think we are done with this. Okay. Is that the one that escaped?
Yeah.
Okay. All right. So let's try. Okay. None found. So we commit changes, and then give it about a minute or so to update. All right. So we'll go back to the algorithm. Takes about a minute to refresh all the pages. Not yet. There we go. Okay, so it's all fixed now. So you can see the empty set notations are back, and then everything up here. This is still using there's still a problem with the vertical bar here. I'll fix that later. And over here as well. All right, give you a few more minutes. Okay, I'm gonna fix the vertical bar also, because I fixed the underscore, but I forgot about the vertical bars. So once again, I'm looking for vertical bars that are not properly escaped. So I'm looking for anything other than a backslash, followed by a single vertical bar. And this is specified in regular expression. I think that needs to be escaped as well when I'm specifying it as a pattern. All right, so that's why. Okay, so these all need to be escaped. Okay, I think that's it, because I cannot find any additional occurrences. So commit changes again. All right. So we still have to wait another minute or so, for everything to update. Okay. So let's go back to the earlier part. There we go. So the vertical bar is properly displayed, and there's something else going on here. We'll deal with that later. But this part is looking pretty good, so I think we are good here. All right, so I do apologize for the confusion because of the formatting. All right, so as long as Q is not empty, we still have another iteration of the loop to go through. And this is the sentence, or this is how we choose a vertex, an element out of Q to consider. So the way we choose V as a choice from the set Q is this statement has to be true. We choose the vertex V so that this quantified expression is true. So now the question is, what is the quantified expression trying to say? So we try to read this step by step. For every W in Q, so the question now is, does that W also include your V? The answer is yes, okay? So W and V can be the same. So for every W in Q, we want this statement to be true. L of V, the one that we want to choose, has to be less than or equal to L of W, where W is really just a variable to loop through every element in Q. So in essence, what we are really trying to say is we are looking for V, vertex V, such that of all the elements of all the vertices in the set Q, V has the shortest path, it has the shortest path to a destination. That's basically how we are selecting V. So let me make sure that everybody understand that part, because otherwise the rest of the algorithm may not make any sense. So are we doing okay so far with that statement? We are selecting V in the set Q such that L of V has the smallest value of all the other vertices in Q. Okay, all right. So the importance of this particular statement is because this is why why Dijkstra's algorithm is known as a greedy algorithm. Okay, it is just, I think greedy is really the wrong adjective. I think it is just optimistic, but that's just me. Okay, so if I have to choose a word to describe the algorithm, I'm just going to say, oh, it's just optimistic. Okay, it finds the vertex that has the shortest path already to expand. Okay, but in terms of actual definition of the word greedy, when we use it to describe algorithms, this is why it is called a greedy algorithm. All right, so once we have chosen a particular vertex in Q to consider, then we take that element out of Q. So we say, okay, we'll make sure that we don't try to look at the same vertex over and over again. So if we are going to look at this vertex, we're going to take it out of Q. And then this particular notation is trying to specify for all the incoming edges to vertex V, we want to kind of go through the following calculation. So let me kind of scroll down a little bit here for the rest of this code. Okay, so for every E, okay, this is just a destination of what we're selecting. So it is WV. W is not a bound variable, but V already is. Okay, we know what V is at this point. So we are looking at all the incoming edges of vertex V, and it has to be an edge that is already in E, otherwise it doesn't make any sense because it's not in this graph. So for every incoming edge to vertex V, we are going to do this, evaluate this comparison. If L of V plus D of E is less than L of W, then blah blah blah. Okay, so before I explain the blah blah blah, what is the significance of this comparison? In other words, what are we comparing? Well, L of something is the length of the shortest path of that something, a vertex, to the closest destination. That is, how the L values are determined, or we want those values to be determined that way. And we know that V has an incoming edge E. Okay, that's how we select that particular edge E. And E is coming from vertex W. So now we are basically saying, okay, if W, vertex W, is to go to vertex V first and then go to a destination, this would be the length of that particular path. Let me say that one more time. V already has a path to one of the destinations, and we think it is the closest, okay? It may not be, okay, but we think it is the closest. Vertex W has an edge going to vertex V. So that means this sum, okay, I'm pointing to the addition here, this sum is the length of a path from vertex W to vertex V and then eventually to a destination. Is that part understood? Yes?
What you're saying is you're taking true length and then just comparing it?
Yes.
And then just determining which one is the smallest and then
Not depending on which one is smaller. I'm trying to see if I have just found a shorter path. Because L of W is a value that we presumably have already initialized earlier. In other words, L of W is the length of the shortest path from vertex W to a destination. Is that okay? And we initialize everything that is not a destination, so the L value of that thing is infinity. Okay? But the other side of the comparison, which is L of V plus D of E, is the length of a new path that we are considering, which is the length of the path from W to V, and then from V to a destination. Is that okay? So we are comparing.
shorter to another node, basically?
We want to see if it is shorter, because if it is shorter, then L of W is not really the length of the shortest path anymore, by definition.
So it's kind of like a triangle. You have to be constantly making sure that this is actually, the second length is actually the shortest path to it.
Yeah. It's not really necessarily a triangle, but you can imagine it as a triangle in general, because when we first initialize the L values, every vertex that is not a destination was initialized to a value of infinity, because we don't even know whether there is a path or not. So that means the first time we get to this comparison, for vertex W, this has to be true. Okay? Because L of W would have been infinity at that point, but L of V, just from the fact that V is in the set Q, means it has a non-infinity L value. So a non-infinity L value plus the distance of an edge, which is also non-infinity. So the entire left-hand side of the comparison is just a particular real number. It cannot be negative, but it's a particular number. So if L of W from initialization is infinity, so that means this has to be true the first time we look at a path from W through V to a destination. But even in subsequent, visit of this particular, comparison, every time this is true, every time this less than is true, that means we have found a shorter path. Is that okay so far? Because understanding the code is actually very important when you're tracing it, because otherwise you have no idea what you're tracing. So understanding the context of why this comparison is important is really important. Okay? So what do we do when we discover a shorter path? Well, the first thing we're going to do is to update what we think is the length of the shortest path, because guess what? We found a shorter path. We found a path with a smaller length, so that's why we're going to use the value of the smaller length to update L of W. So the L of W is still reflecting the length of the shortest known path, to a destination. And then what we do is for each WU, so this is a different variable, instead of V, this is U. So we are basically, what we are doing is we are taking away all the edges in the solution E prime, So E prime is also known as a solution set. Basically, if an edge is supposed to be on the shortest path, of a particular vertex, it'll be in E prime. But now we know it is not the case because we just found a shorter path for W to get to a destination. So what we thought was along the shortest path from W to a destination, they should be removed because the new edge that we should insert is WV. So I know it's a little bit hard to see when you cannot actually see a graph, so that's why we're going to run an example later on. So we remove all the solution edges or all the edges in the solution graph because we just found the shorter path from W to a destination, and then we just add that particular edge into the solution, E prime, and then we say, oh, since we just updated L of W, then we have to include W in Q because everything that connects to W, they also need to be reconsidered. Because, okay, so let's just say that I just found a shorter path. Okay, let's just say that you just found a shorter path to a destination, and I'm a vertex that points to you. Okay, so doesn't that mean that I might actually find a shorter path too? Because you found a shorter path, and I have an edge leading to you. Does that make sense? Okay, so that's the reason why we have to add vertex W to Q, because all the vertices that connect to W can potentially find a shorter path as well. So when we run the algorithm, it'll be clear, okay? And this is it, okay? This is basically it. The solution graph, which is G prime, has exactly the same vertices, but the edges will be E prime, and E prime is guaranteed to be a subset of E. All right, so that's the algorithm. If you have a mobile device or if you have printed out this note here, you can go ahead and just refer to the algorithm when I'm going to do a trace, okay? So what I'll do is I'm going to the shared folder and I create a new spreadsheet to represent the trace of this algorithm. The trace of the algorithm is going to consist of a few columns. So we have to track down what is in the set Q. So Q needs a column. We want to know what vertex we have chosen to consider, which is variable V. And then in the for loop, we also have incoming edges. So W is the first of the two tuple of the edge, V, WV. So that's W. And then we need a bunch of columns for the L value. So we need, we also need E prime. So we need E prime, and then a bunch of columns for the L value. So the L value, there's one column for each vertex here. So we got vertices A, B, C, D, E, F. So that's kind of, these are the columns that we need to track when we run the algorithm. The width, yes, go ahead.
Can you describe these variables again?
Say that one more time.
Can you describe these variables again? Q, E, W, E.
Q is what I call the boundary set. It is, so if you think about breadth first search, okay, is everybody familiar with the term breadth first search? Yes, no, kinda, okay. So remember the cockroach example in the maze? So the deadly gas, okay, the pesticide, spreads at a certain rate, okay? So the boundary set is really representing all the locations, all the junctions, intersections that is just getting gassed. Okay, that's our boundary set. That's what Q is representing. So Q is representing, all the intersections that are just getting gassed because we're performing a breadth first search from every destination exactly at the same time. We're expanding out from all the destination cells. So every destination vertex is a place where a pesticide bomb is located and all the bombs go off at the same time. Is that okay? Does that help explain what is Q?
Are you saying Q can be a set of vertices?
It's a set of vertices, yes. It is a set of vertices because it is initialized to all the destinations to begin with. And then every time we add something to Q, it is a vertex that we just have the L value updated. Okay, so that's the nature of Q. V doesn't need that much space because V is just a vertex, and so it's just a letter A, B, C, D, E, F, and so is W. So these two do not need as much space. E prime potentially can use a lot of space, so I'll give it a little bit more space here. And then A, B, C, D, E, F are really this is columns E to column E to J are each one is representing the value of L of A, L of B, L of C, and so on. So because these two are the only two destinations, so they are the only ones that are pre-initialized with 0. Everybody else will be initialized with infinity. And I cannot remember how to type infinity here, so I just use the word INF to represent the quantity of infinity, which basically means it is greater than any actual value. Okay. E prime is initialized to an empty set. Q is initialized to the set of all the destination vertices. Okay, just from the spreadsheet, do we know which two? Okay, I just gave you a partial answer. Do we know which two are the destinations? E and F, right? Okay, so that means Q starts off with those two vertices. So are we okay in terms of how Q and E prime and also all the L values are initialized? Okay, it might be helpful if you have a mobile device to kind of read the notes, read the algorithm at the same time. But even without that, okay, I hope you recall the earlier discussion. Does anyone want me to kind of flash back to the algorithms just so that you have kind of like a mental picture of where we are at in the algorithm? Okay, so the algorithm is on this side. So we are just done with the initialization. So that means we are done with these two for each loop. We're also done initializing Q, the boundary set, and we're also done initializing E prime, which is the set containing all the edges along shortest paths. Okay, so the fun part about this particular algorithm is it doesn't just discover a shortest path from one vertex to another vertex. It discovers the shortest paths from every vertex to the closest destination. So we'll see how this works, okay? Because I think it's kind of cool. All right. So we are now done with all the initialization, which means we are now into the actual control structure, the loop here. So now the question is, okay, let me see if I can display multiple things at the same time, okay? Because that might make it a little bit easier to read. And first of all, I'm gonna call this using today's date. So for those of you who have a mobile device and you want to look at the spreadsheet, you can do so at the same time. All right, so Q is clearly not empty, okay? Has got two elements in it. So now we have to select which of these two I should use as variable V. So now we go to the algorithm, okay? I keep using the wrong key to get to the algorithm. So now we are into this part of the algorithm. We have to select one vertex out of Q because it has an L value that is the smallest. So which one should I choose? It's a trick question. Because they're both zeros, right? So I can choose either one. So which one do you want me to choose? E or F? It doesn't matter. It should not even matter. E. Okay, so let's choose E then. Okay, so there are two E's because one E is representing the element E, and then the other E later on is representing a local variable edge E. So we'll just put E here. Once you have selected E to be our V, you have to remember to take it out of Q. So if I were to show you which part of the code does that, it will be referring to this part here. So whatever vertex you have chosen to consider, you have to take it out of the boundary set because otherwise we'll have an infinite loop. So now we have to look at all the incoming edges. In other words, we look at all the incoming edges of the graph and you tell me which one you want to consider first. So this is where it might get a little bit tricky. So let me see if I can do something like this. I'll shrink the graph to the point where it is still visible, but it won't take up a lot of space on the screen. So I take a screenshot like this, and then we'll display it with a particular program and make it stay on top. So this way, I can always display this, on the side, so you guys can reference the actual graphical, visual nature of the graph when we, kind of zoom this one back in. So we have chosen E. So can someone tell me what are the incoming edges in this case? Who are the vertices directly leading to vertex E? A, okay, so A is going through an edge that has a distance of 10, B is going through an edge that has a distance of 2, and D is going through an edge with a distance of 6. So those are the three that we need to consider. In the spreadsheet, okay, when I'm tracking this, I'm just going to write down, okay, because I don't want to have to kind of go back and forth all the time. So I'm going to just write down A. Now, it doesn't have to be this order either, okay? So that means when we are considering the incoming edges, it doesn't have to follow alphabetical order. If I want to, I can make it like B, and then D, and then back to A. So that means there are 3 factorial ways to order the consideration of the incoming edges, okay? Which one you choose is entirely up to you, okay? It should not affect the correctness of the algorithm. Okay, so we'll just focus on BE, sorry. So we are looking at the edge of BE, okay, because B is W and E is V. What is L of E? L of E is a 0 right now. Okay, very good. What is the distance of the edge BE? That one you can tell from the graph itself. It is a 2, right? So on the left-hand side of the comparison, we have 2 plus 0, or I should say 0 plus 2, which is 2. What about on the right-hand side? What is the L value of B? The L value of B right now is infinity. So let me point back to the algorithm where we are at. We are evaluating this particular statement, okay? So L of W is B in this case, is infinity because that's how it's initialized. On the other side, L of V is L of E, which is 0. The distance of the edge is 2, okay? So we have 0 plus 2 on the left-hand side, infinity on the right-hand side. So can someone tell me whether it is true that the left-hand side is less than the right-hand side? It is true. Okay, very good. So that means we got a bunch of stuff to update. The first one is to update L of W. So in the spreadsheet, the way that happens is we just go to this column, which is column F, and then we just say, hey, vertex B, we just found a quote-unquote shorter path for you to get to a destination. So that would have a length of 2. And then we go to E prime and go like, okay, erase all the edges that start off with vertex B because all of those are wrong now, okay? We just found a shorter path from vertex B to a destination. You go like, yeah, but we actually do not have a path yet. So E prime is updated, but there's no change to it because there's nothing to remove at this point. But the algorithm later on also says, oh, by the way, after erasing everything that is not on the shortest path, go ahead and add this edge here. So this edge is from W to V. W is B, V is E. So we're adding the edge BE to E prime because that particular edge is now on the shortest path from vertex B to a destination. So now we go back here, and then we go like, okay, now we add BE as an edge to E prime. But since the L value of B just got updated, B has to be added to the boundary set, which is Q. So the set Q now has BF in it. F was already in it. I'm just adding B to it. Is that part okay? Because that basically completes one iteration of the for each loop, where we actually have something to update. D is kind of in the same boat, okay? So D says, oh, okay, L of D was initialized to infinity, but we just found a path of length 6, from D to a destination, so we have to go through the same thing. So the L value of D is now updated to a 6. There's not anything that we need to remove from the set E prime, except we have to add the edge DE, because now we know DE is, at least for the time being, the shortest path from vertex D to a destination. Now, later on we'll discover that D can find a shorter path to a different destination, but right now, this is all we can do to do the update. So now we say, okay, since vertex D has the L value just updated, we are adding it to the boundary set. Yes?
So why are we adding BE to the
To E prime?
say again, sorry.
To E prime, which is
Yeah,
the
or-
name of the set.
For,
Because BE is now, at least currently, along the shortest path from vertex B to a destination.
and then as it goes down, B and that.
Correct.
Okay.
Yeah, because E prime is keeping track of all the edges along the shortest path of every vertex to its closest destination. Yep. All right, so when it comes to A, kind of the same deal, right? Because A had an L value of infinity. We just found a path with a length of 10, okay? So we just put the 10 here, and then we do all the usual updates. There's nothing to remove because we haven't found an edge from A to a destination yet, so there's nothing to remove, except we have to add AE over here. Now, if somebody is complaining and say, but that's not even the shortest path, it just looks like the shortest path, you are correct. So we'll see how the algorithm can figure that out and go like, oh, wait, hold on a second here. There's a better path from A to get to a destination, because it will figure it out. All right, so that completes the for each loop in the algorithm for the first iteration through the while loop. Are there any questions? Questions? Okay. So when you are watching this video, you can kind of consider doing what I just did. Well, okay, it's easier when you're watching this because you can open two windows, right? One window on the spreadsheet that's already done, okay? You just have to keep track of which row we just worked on, and then have the algorithm displaying on the other side. So that means when you're reviewing this material, it is going to be a little bit easier, because you will be doing it on your own computer. All right, so now we go back to the beginning of the while loop, and the first question is, are we done? Is Q empty at this point? It's like, not even close. So now out of these vertices, A, B, D, and F, we have to choose the one that has the smallest L value. And which one would that be? F, that's right. Because the L value of A is 10, the L value of B is 2, the L value of D is 6, but the L value of F is a 0 because F is one of the destinations. Okay, so now we say, let's go pick F here. Now we have to look at all the incoming edges into vertex F. So vertex F is right here, and it has 3 incoming edges. One is coming from B, one is coming from C, and one is coming in from D. So do I have to look at it as B, C, D? The answer is no. I can change the order. I can say C, B, D, or C, D, B. It doesn't really matter, okay? I have 6 ways of ordering these things, and any one of the 6 ways is fine. Is that okay? Because I want people to understand that we don't have to go by alphabetical order at all. Are we good? Okay. So I'll just use this particular order, okay? We'll look at C first. That's an easy one, because C has an L value of infinity at this point, so we have just found a shorter path. So we have just found a path with a length of 8. So now we go update L value of C is 8. And we want to add, we want to remove all the edges from C to something else because all of those edges are not on a shortest path anymore, but none is here because we haven't found a shortest path from C to anything yet. So we just have to say, oh, okay, that means I'll just do the lazier approach, copy, paste, and modify. So we're just going to add C, F, onto E prime. And because C has its L value just updated, I forgot one thing, because I forgot to remove F from Q first. So that one is, so F is gone from Q, but now we have to add C to Q because we just changed the L value of C. Are we okay? So I'm not kind of flashing between the algorithm and the table or the trace. Do you guys want me to kind of flash back a little bit? Yes, no, okay, all right. So now we work on D, okay? So we look at D and go like, okay, did we just found a shorter path from vertex D to a destination? There are two destinations. In other words, okay, this time I do have to go back to the algorithm. I'm re-evaluating, okay? L of D is already a non-infinity, okay? It is what? It was a 6, okay? So it is 6 plus, oh no, 6 is on this side, sorry, I take it back. 6 is on this side, and on this side we have 2. Because we are looking at D and go like, okay, how do we get to a destination? F has a length, okay, F has a shortest path with a length of 0 to a destination. Guess why? Because F is a destination. But we don't even care why that is the case. We just know that the length of the shortest path from F to a destination is 0. That's all we care about, okay? And then we have an edge of distance 2 from D to F. So that means, oh, so if D is to go to F first, and then from F we go to a destination, that would give us a path with a length of 2. And 2 is less than 6. So we have just found a shorter path in order for vertex D to get to a destination. So this is important, okay? I just want to make sure everybody understand what I just talked about. Okay? So in the algorithm or in the trace, okay, in the trace, all we're going to do is to say, okay, we did find a shorter path because that shorter path has a length of 2, and this time I have stuff to do, okay, because the first thing I need to do is to get rid of DE. Okay, so that's the first thing I need to do is to get rid of DE. And then we add the new edge, which is from D to F. Is that okay? So it's a two-step process. We first remove any edge, okay, but there can be only up to one edge starting from vertex D, but we'll just say for every edge that is starting from D in E prime, we have to get rid of those, because those cannot possibly be on the shortest path anymore, because I just found a shorter path going through a different vertex to a destination. And then we have to add DF, because now DF is on the shortest path from vertex D to a destination. So what do we need to do next is to make sure that D is in the set, but D is already in the set queue, so I don't have to do anything here. Is that okay? All right. And then we look at B, okay, so B is right here. And B already has a shortest path of a length 2 to one destination, and now it has another path to a destination again. But this time, the less than is not true. Because if I were to look at the algorithm, this time when you look at this condition, L of W would be the 2, and then L of V is 0, D of E is going to be a 4. So we are looking at 0 plus 4 on one side, and we're looking at 2 on the other side. 4 is less than 2 is not true, so I got nothing to do for this iteration of the for each loop. Because going through F to get to a destination does not yield a shorter path compared to what I have found already, because B already has a shortest path of length 2 to a destination. Is that okay? Because I'm showing you one example where, oh, there's no update because we did not find a shorter path. Is that okay? All right. So now we go back to the trace because there's no update. So now we go back to the while loop. So when we go back to the while loop, we ask the usual question is, are we done? Is Q empty? No, it is not. So now we have to go through this selection process and find a vertex V in Q that has the smallest L value. So I'll let you guys decide which one has the smallest value out of A, B, C, and D actually. Okay, look at the L values of A, B, C, and D. Which one has the shortest L value?
B.
B or D. Okay, so which one do you want to choose? You can pick either one. Okay, I heard D. Okay, so we'll pick D. So that means D cannot be in the set anymore because whatever we choose to expand or explore, we have to take it out of the frontier set. So I call it frontier set, or the what was the other term? Boundary set. Okay, so they're basically referring to the same thing. So now we have to look at all the incoming edges to vertex D. So to vertex D, we have 2 incoming. One is coming from C and one is coming from F. So just to emphasize, we don't have to be alphabetical. We will choose the F first and then the C. It doesn't really matter which way we do it. So we'll look at F first. So the question is, did I just find a shorter path from F, through vertex D to a destination? No. What is the L value of F? It's a 0 because F is a destination. We are already standing at a destination. In other words, you are standing in front of a bathroom and somebody asks you, "What I need to go to the bathroom?" Are you going to tell that child and go like, "Oh yeah, we're going to go through this route here to find the other bathroom," when you're already standing in front of a bathroom? The answer is no. Okay, so that's why there's no update here for sure. What about C? Okay, let's take a look. The L value of C is an 8 right now, which means the length of the shortest known path, the known shortest path, has a length of 8. Okay, so now we say, well, what if I were to go from C to D? What would be the length of that path? So now we have to first look at what is the length of the shortest path from D to a destination. That is a 2. Okay, what about the edge going from C to D? What is the distance of that edge from C to D? You guys tell me. It is a 4, okay? So that means together, the length of the path from C to D and then from D to a destination is going to be a 4 plus 2, which is a 6. So the question now is 6 less than the length of the shortest path known up to this point, which is 8. Yep, we just found the shorter path. Okay, so that means, okay, we got stuff to update here. The length of the shortest known path up to this point is now a 6, but that also means we have to update E prime. Okay, so it's hard for me to display this because I think it is not possible to do a strikeout only on a portion of the cell. When I use strikeout, it strikes out the entire cell. So I'm gonna have to do it like, actually remove this element, and then we add the new edge, which is CD. Okay. But does everybody understand the reason why we have to do this? CF is no longer along a shortest path from vertex C to a destination, because guess what? We just found a shorter path. The new shorter path is going from C to a D. Now from D, where do we go? I don't care, because I only need to know that from D to a destination is a length of 2. That's all I need to know. Is that okay? So that's why we have to keep track of the L values, is so that we can do this kind of evaluation. So after this, we say, okay, since we updated the L value of C, we have to add it back into the set Q, but it's already in the set Q, so we don't have to do any actual update or change to the set Q. Is that okay? Are we still following along in the reasoning of the algorithm? Okay, all right. All right, so now we're back to the main loop, which is asking, is Q empty? No, it still has 3 elements. So now we have to say which one has the smallest L value at this point. So we are looking at vertices A, B, and C. A has an L value of 10, B has an L value of 2, C has an L value of 8. I think B wins. Okay, B is the one that we have to choose.
Did you say that C has a value of 6?
Yeah, you're correct. It is a 6. Sorry. Yep. It is the last update that counts. Thank you. So it's 10, 2, and 6. The 2 wins. Okay, so that means this time we have to choose vertex B to be our variable V. Then we have to say, okay, what are the incoming edges to B? Well, that's a simple one, because there's only one incoming edge to B, which is from A to B. Okay, fine, we'll look at that. All right, So now when we look at the comparison, okay, let me go back to the algorithm. So when we look at this comparison here, now we are basically saying that according to what we have tracked already, vertex A has a path to a destination, and the currently known shortest path has a length of 10. But if vertex A is to go to vertex B first, then the edge from A to B is a 5. But from vertex B to the closest destination, the length is only 2. So that means if A is to go to B and then B is to go to the closest destination, that path is going to have a length of 7. That is correct. 7 is less than 10, so that means I have just found a shorter path from vertex A to a destination. So that means I have to update a bunch of stuff. Okay, so this is now updated to 7. And then this part here, I'm going to do the full edit. So the first thing is to remove all the edges starting with A, because those used to be along the path from vertex A along the shortest path to a destination. Guess what? That is not true anymore because I just found a shorter path. So now we replace that with AB because AB is now on the shorter path. And then we also have to add A back to the set. Okay, I forgot again to remove B from the set queue. So let me do that first. There we go. But the set queue already has A in it, so there's no apparent update because it already has A in it. So now we go back to the top of the loop, which is also asking the same question. Are we done? Is Q empty? The answer is, no, we still got 2 elements in it. One is A, one is B, one is C. So which one should I choose? So we are looking at 7 versus 6. Okay, they're pretty close, but nonetheless, the one is still smaller. So this time we have to choose vertex C because vertex C has a smaller L value. And now we have to look at all the incoming edges to vertex C. And there's none. Woohoo! Okay. But I forgot again to update Q because every time we choose something out of Q, we have to remove it from Q. Alright, so now we're back to the beginning of the loop and we're asking, is Q empty? Not quite, but pretty close because we only got 1 element left. If you only have 1 element left, you don't have to do any comparison because that has to be the vertex that you choose out of the set queue. Okay, cool. Now set queue is empty, but now we have to look at all the incoming edges of A. There is 1. Okay, that's this B to A, which means it has a loop. So is the loop gonna do anything crazy? The answer is no, because we already have found a path from A to B to a destination, and this path cannot be any shorter. Okay, so let's check all the numbers that we have. So this is B. Okay, BA is the only incoming edge that we have to consider. What is the length of the shortest path from B to a destination? 2. If B is to go through A to go to a destination, how long would that path be? Well, A now has the shortest path from vertex A to a destination has a length of 7. And then to go from B to A, it has a distance of 4. 4 plus 7 is 11. So that means if I were to go from B to A and then from A to the closest destination, it would have cost me 11 as a length of the path. However, B already has a path of 2 to a destination. So that means that comparison is going to fail, which also means there's nothing to update at this point. So now we're all done, okay? Because the set is empty because we're not adding B back into the set queue. So the algorithm is done because the next time you go to the while loop, Q is an empty set. So now the question is, what does that mean? Okay, what does it mean that E prime has B, E, D, F, C, D, and A, B in it? So that means BE, okay, BE, this path here, this edge here, DF, which is this one here, CD, which is this edge here, and AB, which is this particular edge here, collectively, they form the shortest paths from any vertex to the closest destination. Is that okay? Kind of, okay. So let me see if I can highlight, the paths, in E prime. Okay, so give me a second here to look up, how mermaid can select, because I want to highlight the edges, so I'm just looking for a way to highlight the edges where it shows a little bit differently because I want that to update. It may not have, okay, let me do a search. I'll do a search on this side where you can see. Okay, so this is the language that I use to describe the graph is called Mermaid, and we want to look at edge styles. Flowchart syntax, I think that's the same document that I was on, so that means there may not be a different way to represent the edges. I'm just looking really, really, really fast. Okay. Well, I can. So instead of changing the style of the arrow, I can kind of make a little star. Use an asterisk to represent that it is along the shortest path. So I'll just go ahead and do that because I don't think there's a way to. This is how we add text to an edge. Oh, we can do dotted lines, but I don't want to use dotted lines. I want to use thick lines, which is equal. Okay, I can do that. All right, so one more update to the document. So go back to the document here. So one more update. This time is on everything along the path of the shortest path is going to be double arrowed. Of course, I cannot remember from the spreadsheet. So BE is one of those. So that means BE, which is this one here, we're going to change all the regular arrow with a bold arrow, like so. And what else? BE DF. Okay, so DF is this one. Same thing. If you don't know how to do markdown yet, it is a useful markup language to learn because you can actually do a lot of stuff with it. You can use it to document your flowcharts. I know you have passed CISP 300 already, but there may be times that you need to show a flowchart to someone else. Okay, so this can be used to display flowcharts, and also for a class like this, you can also use it to show a graph kind of visually. Okay. So this is all done, and I am going to close this and update the original document. Give it 2 minutes, okay? That's kind of like the bake time to get it ready. But meanwhile, we can kind of go back to the algorithm and see if you guys have any questions about the trace and how it relates to the algorithm. The main algorithm is from this while, okay, because the earlier part is just the initialization. And the outcome of tracing this algorithm is displayed here by this particular spreadsheet, which you already have access to. So do we have any questions about how this particular algorithm was traced? No questions? Yes, go ahead.
Maybe not exactly about the tracing of it, but I noticed that the output is itself a graph.
Mm-hmm.
Is it just is basically pruning off all the ones that weren't part of the shortest path, right?
Yeah, it's just removing all the ones that are not along the shortest path,
Okay.
along any shortest path, I should say. Now, if there are two shortest paths of the same length, then the algorithm would discover one but not the other. Because the update, okay, when you look at the actual update, it's only looking for less than, but not a less than or equal to. But if it's a less than or equal to, it means the first path is destroyed when you update it with a second path of the same length. So it does not find duplicate paths, which also means one thing. What is the property of a tree? What makes a tree not a general graph? What are the rules that dictates, oh, this is a tree, but what qualifies a graph as a tree? Sorry? Okay. But what is one way to describe that? So let's just say that the direction of the edges are always from a parent to a child. Okay, so from the root to one of the nodes of the root. So if that is the usual direction, what is one way to describe a tree?
A child connects to another child or back to a parent.
Well, first of all, each node or each vertex or each node in the tree can only have one incoming edge, up to one, because the roots have none. Is that okay? So that's one requirement. Okay, so I'm pretty sure the baking is all done. So we're gonna go all the way to the graph representation and look at the update. So the bold edges are the ones in the solution. So that means you can start with any vertex, okay? A, B, C, D, E, or F, okay? And you can say, tech, show me, what is the next step I should take in order to end up at a destination. Pick one, okay? I will let you guys pick a single vertex, and I'll tell you how to get to a destination in the shortest path. Pick one. So from A to F. Sorry? A, okay? So if I look at A, it only has up to one outgoing edge. In this case, it is the 5. Okay, the one that has a distance of 5. So that means of the 2 optional ways to get out of vertex A, I should take this one, from A to B. Okay? So what about, okay, someone can pick a different vertex. Go ahead and pick a different one. Vertex C, okay, this is vertex C. It has 2 outgoing edges, which means I do have a choice, but in the solution graph, okay, E prime only has the edge from C to D. So that's the edge that I'm gonna take. That will lead me to a destination in the shortest path. Does it make sense though? Yep.
So does that mean that there's going to be a tree?
This is okay. This is not a tree, right? Because you can see how it is not a tree because D and E are not connected.
Okay, there's
Okay.
many trees.
Yes, there's a name for that, many tree. What do you think is the name for many trees?
Forest.
It's a forest, exactly. So a forest is not. I'm not joking. Okay, I'm not just kidding and say, well, since it has multiple trees, let's call it a forest. That is a technical term. When you have a collection of trees, it is called a forest. So which way should I look at this tree? Is every vertex a root, or is each destination a root? Is the destination. Every destination is a root. Okay, so when you look at when you look at F as a destination, it's a root, but we have a really kind of deformed graph here, because this is the root, this is the child of the root, and this is the child of the child. Okay, when we look at the other tree, it's kind of the same deal. Okay, this is the root, this is one level below the root, and this is 2 levels below the root. So both of these are deformed trees, which means we don't have multiple children pointing to the same parent, but hey, it is still a tree. Question?
Just, so the arrows suggest that nothing actually directly goes to C. Does that make C a parent?
So it depends on how you look at it. So from the perspective of how we construct E prime, C is a child. It is a child of D, and then D is a child of F. In other words, from that perspective, we're looking at every destination as a root and ask, okay, so which vertex directly connects to a destination will see this edge as the shortest path. So which one you identify as a root really does not matter. But you can also see, how if I change the graph a little bit, then you can have two vertices going to the same vertex and they both go to a destination. That is entirely possible, but not the other way around. Because you cannot have two exiting edges in the solution, but you can have multiple incoming edges in the solution. Mm-hmm. All right. So, well, it's just the right time too, okay? When you go home and try to study this, okay, because now that we have an example and the trace to go along with it, the focus, okay, there are two different ways to focus on studying this material, and I'll show you what those two different focuses are. One is a mechanical. You're basically just looking at this code here and you're just mechanically saying, okay, this is what we need to do, this is what we need to do, this is what we need to do. That approach works, but it's not the best way to do it, okay? Because it's easy to make a mistake and not know that you have made a mistake. The other way is to think about why are we doing this, okay? How does this step contribute to finding the shortest path? And try to reason out why are we making this comparison? What is the significance of whether this comparison is true or false? What does it mean if it is true? What does it mean if it is false? So look at it from the semantics perspective, I think is a better way to do it. I try to comment the code a little bit here, but you can certainly add additional comments or change the comments to how you would describe the rationale in a particular statement. So I think that is a better way to study the algorithms, is to understand why are we doing this, what problem are we trying to solve, and how does this contribute to the solution. So if you think from that perspective and make use of the trace too, okay? Make use of this trace. Make a copy of this. Go to File, go to make a copy, or if you want to download and do your own editing in Excel, that's all fine, okay? But you can actually add your own comment to the additional columns here and basically just explain what just happened. Why is this happening? And what does it do in the grand scheme of things in the algorithm? So those are the different ways to study these algorithms. I will give you a homework assignment on Dijkstra's algorithm on Wednesday. Okay, so I want you guys to have a little bit of time to kind of absorb what we talked about today before you get the homework assignment. I know we have Thanksgiving right after Wednesday, so I'm not going to make this due on Monday. Okay, that would be kind of cruel, but I can make it due on next Wednesday. Once you understand the algorithm, mechanically tracing through the algorithm should not take a whole lot of time, okay? But it's the understanding of why we are doing this, how it is getting the job done, that might take a little bit of time. All right, so that's the end of today's lecture. Perfect timing today, and I'm gonna stop the recorder and upload the video.